So we're going to get into chapter 12 here, which is chemical bonding. And we're going to talk about really the two types of bonding in this chapter here. We'll talk about ionic bonding, which is always between a metal and a non-metal. And pretty much always when you have a metal and a non-metal together, what will happen is basically the metal will transfer its electrons over to the non-metal. And the result of that is we will create a positively charged cation and a negatively charged anion from the non-metal. And it is the attraction between these two guys that basically hold that together. There's absolutely important with ionic bonding. Again, no sharing of electrons. There's a complete transfer of electrons from one to the next. And that's different than covalent bonding. And in covalent bonding, it typically is two nonmetals. And here we have some aspect of sharing of electrons, which is really what holds that guy together. As we'll talk about here in this chapter, the sharing may be equal sharing. It may also be unequal sharing. But in a covalent bond, there's some aspect of sharing that is basically occurring. So let's get into some of these. The way that we kind of represent bonding is we do use what are known as Lewis dot symbols. And Lewis dot symbols are also sometimes just generically called electron dot symbols. And they basically show the number of valence electrons that each atom has. And valence should have an E. The number of valence electrons are the valence electrons in for the outermost electrons. They're the ones in the highest energy level. They're the ones that are involved in bonding. And a very easy way to calculate the valence electrons is that it is equal to the group number. So everybody in group 1 has one valence electron, everybody in group 2, 2, 3, 4, 5, 6, 7, and 8. The only exception would be helium, which is part of group 8, but that is helium, which has only 2 total electrons, so it could not have 8 valence electrons. So helium has 2 valence electrons. Everybody else in group 8 will have 8 valence electrons. There's no real strong rule about Lewis dot symbols in terms of how you draw it, other than it typically is the symbol and basically dots to represent the number of valence electrons that there are. Their one rule, I guess, would be is you typically do not put more than 2 dots per side. So there are 4 sides. That's a total of 8 electrons. And once again, that 8 is a magical number in sort of bonding. It is basically the number of electrons that group 8 has in terms of valence electrons. And that is really, as we might have talked about before, the basis of all bonding is for everybody to achieve basically the same electron configuration as a noble gas. And that's really the basis of everything in terms of bonding. And that's why 8's a really important number sort of in bonding. It allows people to get to that electron configuration. I think we might also talked about it before. When we talk about that occurring, we're not talking about changing the element into a noble gas, but we are just changing the number of electrons that they have. So it is very similar to the noble gas. They are still the same element because they have the same number of protons, but the electrons are different. So here's a little table I made of some Lewis dot symbols. Again, you can see everybody there in group 1 has 1 dot, 2 dots, all the way down to our 8. Once again, there our helium only has 2 total electrons, so it obviously has just 2 dots that are happening. So we could use Lewis dot symbols to help us understand really the 2 basic types of bonding. Ionic compounds, which you pretty much can identify solely by what is made of. And as I mentioned earlier, that is our metal and non-metal combination. and covalent guys, which are typically two nonmetals together. Now, things with low ionization energy. Ionization energy is the energy that's required to remove an electron. So things with low ionization energy, it doesn't take a lot of energy to actually remove an electron. Things with really high ionization energy, it's very hard to remove an electron. So on the periodic table, ionization energy actually increases as you go up and to the right, and decreases as you go left and down. So nonmetals have very high ionization energy. It's hard to remove electrons from them. Metals typically have low ionization energy, so it makes it easier for them to lose electrons or have electrons removed from them. Also, high electron affinity. Electron affinity is the energy change that occurs when an element gains an electron. And if you just think about affinity, if you have an affinity for something, you usually like it. So there's things that like to gain electrons. On the periodic table, up and to the right, electron affinity increases. Left and down, it decreases. So once again, up to the right, we have things with high ionization energy and high electron affinity. That all leads to those guys, the non-metal region, wanting to gain electrons. Left and down on the periodic table, we have low ionization energy and low electron affinity. And that pretty much means take my electrons, please. They don't really want to hang on to their electrons. It's really easy for them to remove their electrons. So we could use these rules to help us understand that typically our ionic compounds are going to come from elements on opposite sides of the periodic table, which is pretty much our metals and our nonmetals. And what happens when we get guys on the same side of the periodic table, like two nonmetals together, the best that they will do is pretty much go, we'll share electrons, because we both basically want electrons. I'm not going to give away my electrons. So they want to kind of share electrons. So let's take a look at an example of ionic bonding and how we could use Lewis dot symbols to help us sort of understand what is going on. If we look at lithium fluoride here, lithium is a metal, and fluoride, which is fluorine, is a nonmetal. And by the way, once again, once you see that double combination there, it is automatically going to be ionic. So always metal, non-metal, going to be an ionic compound or an ionic bond. If we look at lithium, lithium is group 1, which means it has one valence electron. If we write the electron configuration for lithium, it is 1s2, 2s1. And by the way, that would be the valence electron right there. It is the highest energy level. Fluorine is group 5, which means it has, group 7, which means it has 7 valence electrons. And if we write the electron configuration for fluorine, it is 1s2, 2s2, 2p5. In this particular case, what's going to happen is, because lithium has all the properties of, you could take my electrons, I don't really want to hang on to them, and fluorine has all the properties of, I would like your electrons. When these two get together, the lithium will pretty much shuttle its electron over to the fluorine. The result of that is lithium will now make a +1 charge as it lost the electron. Once again, it loses its valence electron, which is this guy here. And it will end up at a configuration of 1s2. The fluorine will pick up the electron and fill out. And because it picked up one electron, it will become negatively charged. And its configuration will end up being, that electron will end up right there in that p subshell where it has room, and it will be 1s2, 2s2, 2p6. The drawings on the right-hand side here do need to have charges because these are ions, so you do need to indicate the charges. Typically, people put brackets around at least one thing, like the negative guy. Sometimes people put it around all, but to indicate that there's absolutely no sharing of electrons here. So what is holding this together is the positive and negative attraction between the two ions. Let's also look at what happened here in our electron configuration. 1s2 is 2 electrons, and on the periodic table, 2 electrons is helium, yeah, which is a noble gas. 1s2, 2s2, 2p6 is 10 electrons on the periodic table. 10 electrons is neon, which is basically also a noble gas. So these two guys here both achieve noble gas configuration by sharing electrons. I'm sorry, by transferring electrons in this case, by transferring electrons. They become what is referred to as being isoelectronic with the noble gases. That means they have the same electron configuration. And that again is really the basis of bonding here. Any questions on that type of bond there? Now, if we look at another example here, let's take a look at calcium and oxygen. And by the way, that again unit is held together by electrostatic attraction, which is an ionic bond. I think we've mentioned it, but the strength of an ionic bond does increase with charge. So something that is +3, -3 will be held a lot tighter than something that is +1, -1. So the actual charge does play a role as to how strong that attractive force is. If we look at calcium and oxygen, or our calcium oxide here, this is a metal, this is a non-metal. So once again, I know this is going to be ionic. If I look at calcium, which is group number 2, my calcium has 2 valence electrons with an electron configuration of argon 4s2, R1s2, 2s2, 2p6, 3s2, 3p6, 4s2. My oxygen, which is group 6, has 6 valence electrons in this case, and it has an electron configuration of 1s2, not a heart, 1s heart. That's that new electron configuration. All right, let's try that again. All right, 1s2, there we go, 2s2, 2p, where are we at there? 4, there we go. All right, at this point, what's going to happen is kind of the same thing. We have our metal and non-metal together. Our metal is going to give away its electrons, so it's going to send over an electron there. It's going to send over an electron over there. And in this case, at that point, our calcium will now become +2 charge. Our oxygen there will gain the 2 electrons and really complete its octet. And because it gained 2 electrons, it will now get a -2 charge. And once again, it is that +2, -2 attraction that's holding that together. Our valence electrons here in calcium are these 2 right here. And these are the 2 that are lost, which leaves a configuration of 1s2, 2s2, 2p6, 3s2, 3p6. That is 18 on the periodic table, which is argon's configuration. That's what the little brackets and the AR in the middle means. It's argon's configuration. The oxygen has room for those 2 electrons right there in the p subshell. So it will pick up those 2 electrons and go 1s2, 2s2, 2p6, which once again is 10. And that is the same as neon's configuration. So once again, here we see that both calcium, by losing electrons, able to back up on the periodic table to the noble gas that comes right before it. We see oxygen gain the 2 electrons, be able to go forward on the periodic table to the noble gas that comes after it. Once again, they both achieve noble gas configuration, and they're both very happy, obviously, in this situation. Any questions on that? Yeah. It would end up the same. If your question, yeah, in this case, the sulfur would just pick up the 2 electrons and it would end up the same. Yeah. Yep. Other questions? Because again, sulfur and oxygen, again, in the same group, would have the same number of valence electrons, so it'll be able to kind of pick it up the exact same way. Yeah. So let's take a look if we actually combine maybe 2 things we just did, which is if we take our calcium, which has its 2 valence electrons, And it's got its 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And we take a fluorine here, which is 1s2, 2s2, 2p5. So at this point, what's going to happen is our calcium is going to take an electron and send it over to fluorine. At this point, can the fluorine here take any more electrons? It cannot, right? It just basically filled up with 8. Is that going to make calcium happy by only losing 1 electron? And the answer is, if we look at the periodic table and calcium just loses 1 electron, it backs up to potassium, which is not a noble gas, right? So it doesn't want to do that. It actually wants to get back to, again, the noble gas. So it needs a way to lose the second electron. In this case, the 1 fluorine is not enough to do that. So we actually need 2 fluorines here, where the second fluorine now has a spot for the calcium to actually lose a second electron. The result of this is the same for the calcium. The calcium will now end up with a +2 charge because it was able to lose 1 electron to each of the fluorines. Each of the fluorines picked up just 1 electron, which means it has a -1 charge, and we would have a second fluorine that has a -1 charge. And in this particular case, what happens is, in terms of the electron configuration, is the calcium once again was able to get rid of its 2 valence electrons, which are those, leaving it with its 18 valence electrons, which means it again was able, in this particular case, to achieve argon's configuration. Each of the fluorines basically pocketed 1 electron there in the p subshell, giving each fluorine now 10 electrons, and giving each of these guys the same electron configuration as neon. So all 3 of these guys, the calcium, each of the fluorides, which are the guys with the -1 charges, all 3 of them have now achieved noble gas configuration, and they're perfectly happy that way. That is why, if you remember, I think in an earlier chapter, we were talking about ions, and when we put something that's positive and negative together, it needs to equal 0, right? And really the reason why it needs to equal 0 in the simplest way is it allows everybody to achieve the noble gas configuration. That's why when we take a calcium ion and a fluoride ion, we actually need 2 of these guys to give us the proper formula here. And really, when we do that and we kind of put them together to equal 0, what we're really doing is allowing each of those guys to achieve noble gas configuration, which is really what they want to do. So that's really the reasoning behind when they tell you positive and negative guy, put them together to 0, is to get everybody to the noble gas configuration. Any questions on ionic bonding and how to show it? So this, what we're drawing here, is ionic bonding. Whenever you draw anything that's an ionic bond like this, you should always, again, include the charges. You don't have to include the electron configuration. That was just for us to see what was going on. But you should include, obviously, the charges and the dots and that type of stuff. Any questions on ionic bonding here? All right, then let's talk about the other type of bonding, which is covalent bonding. And covalent bonding is always between really 2 nonmetals. So this is between 2 nonmetals. And this is where the sharing of electrons happen. So as we will talk about here, the sharing of electrons can be equal sharing and it can be unequal sharing. So there's really kind of 2 types of covalent bonds, one where the electrons shared equally and one where they are shared unequally. And they both are sort of under the umbrella of covalent bonds. And they do have some different names. Our guy Lewis here came up with an idea of bonding as sort of the sharing of electrons. So when we take something like 2 hydrogen atoms together that each has 1 valence electron, because they're really, in this case, the same element, they both pretty much have the exact same sort of periodic trends. They both want to either lose electrons, gain electrons the exact same way. So nobody's going to really budge in this case. So what happens when you get really two nonmetals together, as I mentioned, they both really want to hang on to their electrons. So the best that they could do is just agree upon we will kind of share the electrons, rather than what we saw with ionic bonding, where we have metals and nonmetals, which have very different sort of theories on electrons. Metals don't really want to hang on to them. Nonmetals want electrons. So here they will basically share, and we can represent that sharing of electrons as basically a couple of dots of electrons there between the two atoms. And what holds those electrons sort of in place is they are negatively charged. So the electrons in the middle are attracted to the nucleus of the hydrogen on the left, and the electrons on the middle are attracted to the nucleus on the right. So it kind of locks them into place between the two. It also means that they count for the hydrogen on the left, which gives this hydrogen 2 electrons. Also counts for the hydrogen on the right, which gives this guy basically 2 electrons as well. You could also represent this sort of bond with a line. So you could draw a line instead of the dots. And every time you draw a line like this, which is, by the way, a single bond, it represents basically a pair of electrons or 2 electrons. Why is this important, say, for hydrogen? Hydrogen actually shared electrons and got to 2. When we look on the periodic table, what element comes after hydrogen? Helium, and helium is number 2, and helium is a noble gas. So hydrogen actually just needs to get to helium to be happy, which means hydrogen should always only have pretty much a line, which is 2 electrons and a hydrogen. You should never, ever, 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 one more time, ever, never find yourself putting dots around hydrogen, because that's going to give you a big X. Yes, it is definitely wrong. You should never like double bond hydrogen because it kind of looks cool, or triple bond hydrogen because it looks cooler, or triple bond hydrogen and put dots around it. You should never do any of those things because they are all wrong. Yeah. I've seen all those things on tests and stuff like that. So don't do any of those things. So it's a really important thing. And it's a very common thing because we're all just, as we go through this, we're used to like putting dots on things, and then you just kind of throw dots on hydrogen. Never, ever should have it. The only time hydrogen can have a dot is if you choose not to use a line. You could use dots to represent the bond, you know, but other than that, they should not have more than 2 electrons ever. I think I made my point there. I hope. Yes. All right. So in a covalent bond, as I mentioned, is that really mutual attraction between the shared electrons and the nucleus that sort of locks, again, everybody into place. So if we look at an example of fluorine, for example, here, fluorine, which is group 7, has 7 valence electrons. And obviously another fluorine here would have 7 valence electrons. Once again, what we're going to get is these two guys, because they're both nonmetals, really sharing those electrons. And we will end up with a fluorine that looks something like this. And once again, you can represent sort of the bonding electrons with a line. So you can draw it like this, which is perfectly fine as well. And in this particular case, what ends up happening, if we look at those electrons in the center, they do count for the guy on the left, which gives this guy on the left 8 electrons. Counts for the guy on the right, which also gives this guy 8 electrons. And once again, here, by sharing electrons in a covalent bond, we're able to get both of those elements over to basically the noble gas configuration, which makes them really, really stable. Any questions on that there? And again, like I said, you can draw it either way. If you like all dots, you could use all dots. Personally, for me, for the bonding there, I use lines, but you know, if you want to use dots, it's okay as well. Any questions on that there? So there are some different types of electrons when we look at a picture like this. All of the dots here, which are really not involved in bonding. As you can see, there's no other element pretty much there. Those are what are referred to as lone pairs, although a lot of books nowadays, most books, I think, use non-bonding electrons. So non-bonding electrons and lone pairs are basically the same thing. They are really electrons that are not involved in any type of bond. Obviously, in the middle there, where we do have electrons that are involved in bonding, it also has a creative name. It is known as bonding electrons. Yeah. So bonding electrons, much like the name implies, is involved in a bond. And it really is the bonding electrons that you could show either as a line or dots. The non-bonding electrons are usually always shown as dots, unless you're an organic, and then they like to draw little lines, but you should use dots in most cases for the non-bonding electrons. Whenever you draw your Lewis structures for covalent bonding, you should always show both. So you should always show all the non-bonding electron, the dots. That's, again, a very common thing. Sometimes people just leave off the dots, you know, so you got to show all those non-bonding electrons and also obviously the bonding electrons as well. It's important to remember that we do show a Lewis structure represented with our dots and our lines. It does only show a certain number of electrons. It really just shows those valence electrons and not the other electrons that are there. So for example, something like fluorine 1s2, 2s2, 2p5. These here, which are the highest energy level, and that's because they come at the 2, right? That's basically the n equals 2 level. That is going to be the valence electrons. The lower energy level electrons, which are closer to the nucleus, are what are referred to as core electrons. And they're not involved in the bonding because they're frankly closer to the nucleus, which means they're like kind of sitting right on the positive charge, or they're held very, very tightly. It's an enormous amount of energy to try to remove those, and it really doesn't happen all that much ever. So really, it's just those valence electrons, which are further away from that positive charge, not held as tightly, and they're able to be shared and kind of lost in other cases. We only really show the valence electrons, obviously, in our Lewis structures. Here's another example of water. And once again, here with water, we're able to see the oxygen and also the hydrogen by sharing electrons here. They are able to basically reach their need. The oxygen by sharing electrons with both hydrogens is able to get to 8. This hydrogen by sharing with the oxygen gets to 2. And this hydrogen by sharing with oxygen gets to 2 electrons. Again, getting us to the 8 for everybody other than hydrogen, and getting hydrogen to 2 through the sharing of electrons in this case allows everybody to be really happy here in this bonding situation. So that brings us an important rule that we've sort of been talking about, and officially it is the Octet Rule. And the Octet Rule, much like the name implies, is everybody in bonding, and especially covalent bonding, they will continue to make bonds until they pretty much have 8 valence electrons around them. The exception, again, is hydrogen, which, as we talked about, really should only have 2. And that is sometimes referred to as the duet rule, that gets hydrogen to 2, basically. But everybody else will do 8. Later on this chapter, we'll talk. There are some exceptions to the Octet Rule, but the main rule that you should try to achieve in most cases is that 8 valence electrons around it. Now, sometimes that requires sort of a single bond to do, and you could get everybody to 8 with just single bonds. Sometimes that requires double bonds to get to 8, and sometimes it requires triple bonds to get to 8. And we'll talk about sort of the order at which you should try to draw these things. And the order is you shouldn't double bond and triple bond out of the gate, which a lot of people really like to do. You should really save double bonds and triple bonds to sort of fix things. So usually the good approach is kind of single bond things and then get into double bonds or triple bonds if necessary. A single bond, as we see here with our fluorine, once again can be represented by one single line, which represents a pair of electrons, or obviously 2 electrons. And as we talked about before and counted, by sharing our electrons here, each of these guys get to 8. In something like CO2, which is below, the carbon actually needs to double bond out with the oxygen on both sides. And by doing so, the carbon there ends up with 8 electrons, 2 for each line, basically. And each of the oxygens end up with 8 electrons, once again, 2 for each line, and our non-bonding electron pairs as well. So in this case, something like CO2, it needs to double bond to allow everybody to kind of share the 8 electrons. And in the case above, it doesn't need to do that. It just needs single bonds to get you there. And obviously, a double bond would be represented by 2 lines or 2 pairs of electrons, or a grand total of 4 electrons total. That also means that in some cases, things do need to kind of go to the triple bond route to get themselves to that good situation. And something like nitrogen is an example of that. It does need to triple bond. A triple bond is represented by 3 lines, or 3 pairs of electrons, or 6 total electrons. And as we can see here, by this nitrogen triple bonding, it ends up with 8. And so does this one. On the bottom here, the carbon triple bonding ends up with 8 on both of those. And once again, our hydrogen, by actually bonding as well and sharing, gets itself to 2. So once again, as I mentioned, that is the whole goal of bonding, is get everybody to that 8 electrons, that noble gas configuration. That's really the purpose of what's going on here. Any questions on that there? So when we're talking about sharing electrons, how do we know if the electrons are going to be shared equally or unequally? Really, the biggest factor is electronegativity. Electronegativity is the ability of an atom to bring electrons towards itself. And when we look at the periodic table, also known as a box here, it increases as we go up and to the right, electronegativity, and decreases as we come down, with fluorine being the most electronegative element you could have. So fluorine is the most electronegative element you could have. If you look at the periodic table, that's pretty much as far up and to the right as you could go. The only wise past fluorine is noble gases, which are chemically inert. They're fine. They're really not looking to bond or anything like that. So that is the most electronegative element that you could have. So when we look at a bond like we've seen, say, between 2 hydrogens, because those hydrogens are obviously the same element in this case, we would expect the electrons to be attracted to this hydrogen pretty much the same way that it's attracted to the hydrogen on the left. If my green smear, there's the electron attraction. And the same thing here if we had our fluorines that we also saw earlier. You know, each of these are fluorines, which means each of them are going to have pretty much the exact same pull on those electrons in the center. And we would expect, you know, the electrons kind of pulling towards the fluorine would be kind of the same as we got going on towards that fluorine. The result of this is the electrons in this type of bond would be thought of as being shared equally. There's going to be kind of an equal pull towards both of the elements that are here. The electrons will be shared equally. And when we share electrons equally, this is what is referred to as a nonpolar covalent bond. Or frankly, most people just leave the covalent part out and call it a nonpolar bond. So most people just call it nonpolar, kind of leave the covalent part out of it. The end result of equal sharing of electrons is this: within that type of bond, there pretty much is no side that's more negative. There's no side that's more positive. It's almost like a neutral bond. There's like nice, perfect equal sharing of those electrons. They're distributed over the bond equally. So there's no buildup of charge on any side. And you can kind of think of it as a neutral sort of bond. Now, what happens though if we take out, say, a hydrogen and we place it with a fluorine? Now, based on electronegativity, which one should be more electronegative here? It is the fluorine, is further up to the right. And what's going to happen with the electrons is, instead of being shared equally, it's going to go, I would like to kind of come over here to the fluorine side. And we'll just have a little bit kind of hanging out over there on the hydrogen side. The result, if all my electrons decided to go vacation over there with the fluorine, would the fluorine side be more positive or more negative? Should be more negative, right? Electrons are more negative. So if they're moving towards the fluorine side will actually become more negative and actually becomes what's referred to as being partially negative. And that's a delta negative symbol there. And the hydrogen, because the electrons are moving away from it, becomes partially positively charged or delta positive. It can also be represented with what is sometimes referred to as a dipole arrow, where it points to the side that's more negative, and the back part that makes like a positive sign is to the side that's more positive. So without the plus and negative on that arrow, you can just draw the arrow pointing to the side that's more negative, and that represents it. So when we get this sort of unequal sharing of electrons in this case, this type of bond is what is referred to as a polar covalent bond, or just a polar bond. So nonpolar bond, equal sharing of electrons. Polar bond, unequal sharing of electrons. The result, once again, of a polar bond is we actually do get some charges developing here. One side is more negative, one side is more positive. Why is it only a partially negative charge and a partially positive charge? Why is it not like a full negative charge and a full positive charge in this case? Exactly. So there's still some aspect of sharing that's happening here, right? So even though the hydrogen is almost losing the electrons, it's still like hanging on. So there's still a little bit of sharing that's actually happening in this case. So that's why we get only a partially negative charge and partially positive charge. And that's different than what we see in an ionic compound. In an ionic compound, we get the complete transfer of electrons from the metal to the non-metal. And the result of that is the metal completely loses an electron and becomes fully positive charged, however many lost. And the non-metal will completely gain the entire electron and become more negatively charged, depending on how many it got. But since we are still have some aspect of sharing here, it's only a partially positive and partially negative charge. Any questions on that there? So once again, that is a polar bond, unequal sharing of electrons. And again, that's sort of what we drew earlier, and the way the arrow points. Once again, always points to the more electronegative side, and this guy always to the more positive side, or at least the electronegative side when you point it there. All right. So to sort of summarize the three types of bonding we talked about so far, on one end of the extreme, we have our ionic bond. And that is, once again, always between a metal and non-metal, where our metal transfers the electron, resulting in our cation, which is positively charged, our anion, which is negatively charged. The no sharing of electrons here, but the opposite attract holds that together. So an example would obviously be something like sodium chloride is an example of that. On the other end of the extreme, we have a nonpolar bond, or a nonpolar covalent bond. That is between two nonmetals. That is equal sharing of electrons. And that is something like our H2F2 sort of example. And then sort of in the middle of the two is a polar bond, or a polar covalent bond. And that is also, again, between two nonmetals. And this is unequal sharing of electrons, which results in an example like this, where we do get those partially positive charges, partially negative charges. So one end of the extreme, like we just talked about, complete transfer, electrons go from one to the next. always with a metal, non-metal, that's always what's happening. On the other end of the extreme, we got two nonmetals that are going to kind of nicely equally share those electrons, create sort of a neutral bond, if you will. And then in the middle, we don't have such equal sharing of electrons, but we don't have such unequal sharing of electrons that they've traveled from one to the next. There's somebody still hanging on, but it's definitely not equal sharing of electrons, resulting in our partially positive and partially negative charge. Any questions on the different types of bonding? Once again, these two here are covalent bonds, and obviously this is an ionic bond. Yeah. So what helps us really decide, when we do get two atoms together and between those two atoms, are those electrons going to be shared equally or unequally? It is the electronegativity, which is really what we look at to help us determine, I think they're going to share them equally, or I think they're going to share them unequally. It is related to electron affinity, which is the energy change that occurs when somebody gains an electron, and ionization energy, which is the energy required to remove an electron. So something like fluorine has high electron affinity, high ionization energy, has high electronegativity, which is 1O, I think. And something like sodium has low electron affinity and low ionization energy and a low electron affinity. Again, this goes back to basically nonmetals. Pretty much their whole game is they like electrons and want to get electrons. Nonmetals don't really want to hang on to electrons, or are willing to let them go, basically. So a guy by the name of Pauling, he did a lot of things, but one thing that he did was he came up with a scale for electronegativity, which runs from 0 to 4. And 4 is the most electronegative element you could have, and 0 is obviously not so much. Yeah. So as we talked about, electronegativity increases as you go up to the right periodic table, and decreases as you go down to the left. We could actually use the difference in electronegativity values, which we'll see here in just a second, to help us decide what type of bond it is. So sometimes it's referred to as the change in electronegativity values, or delta En. If you subtract the two numbers and you get anywhere from 0 to 0.4, that is considered a nonpolar bond. So equal sharing of electrons. If you basically go above 0.4, so we'll call it 0.5, to below 2, that is going to result in some type of polar bond, which is unequal sharing of electrons. And typically, if you go above 2, and not in all cases, but that will result in an ionic bond. I'll be truthfully honest with you, you don't even need the electronegativity value table or numbers to determine if it's ionic. All you need is that's a metal and a non-metal together, it's ionic. That's pretty much all you need. You could use the values, and the reason I say that is because you could take two electronegativity values for a metal and a non-metal and subtract them, and you can get less than 2. And it's still going to be an ionic bond. So the 2 number for ionic is sort of a rough cutoff. There are some combinations as less than 2, but they're still ionic. So the best thing to think about for ionic is metal, non-metal, ionic. Don't even worry about electronegativity values, and you'll always be probably right in every case. Really, we use electronegativity values a lot of times for covalent bonding and sharing of electrons between two nonmetals. It really does help us sort of decide that. And here's a table of electronegativity values, and we see the general trend as we go up to the right, it increases. As we go down to the left, it decreases. So if we take a look how to use this, if we did some of our examples like our sodium chloride, we would just go to the table and find the two values. So sodium is 0.9, chlorine there is 3, I believe. And in this case, we just subtract the larger number from the smaller, so we get a positive. So 3 minus 0.9 is 2.1. 2.1 is above 2, so we will know that this is going to be an ionic bond. Once again, we don't really even need the numbers because that's a metal and non-metal. It should be ionic, but you could do it as well. If we look at our F2 that we also saw, our F2, fluorine is 4 and fluorine is 4, which means when I do the difference in electronegativity, that is 4 minus 4, which is 0. and that falls under the 0 to 0.4 category, which means this is a nonpolar bond, and the electrons are being shared equally in this case. A note about an electronegativity difference of 0, you will sometimes hear people call it a pure covalent bond, which is a fancy way of saying that's like perfect equal sharing of electrons. It's still a nonpolar bond, but sometimes people will refer to it as a pure covalent bond because you have the perfect equal sharing of electrons. The reason for that is the nonpolar goes from 0 to 0.4, right? 0.4 is still considered nonpolar and equal sharing of electrons, but in reality, is it perfect equal sharing if it's 0.4? It's not, right? There's a hedge of not equal sharing happening. So anytime you get a perfect 0, it's definitely a nonpolar bond, but sometimes people will refer to that as like a pure covalent bond because it's perfect equal sharing of electrons. If we do our HF, which we looked up there, that's a 2.1, that's a 4, that's a lot of math there, but that is like 4 minus 2.1. I can go with a 1.9 difference there. 1.9 is above 0.4, below 2, which means this is polar. And there is degrees of unequal sharing. This is a pretty big unequal sharing degree, right? As 2 is sort of our rough cutoff for the electrons are going to transfer. So this is like hydrogen is like barely hanging on to it, right? Kind of deal. The fluorine obviously going to be more negative in this case. We would obviously draw the dipole arrow pointing to the side that's more electronegative. So it would point in this case to the fluorine to indicate that. Any questions on that there? Yeah. So I think your question is, do you do it for all 3 elements and something like that? Is that what you're asking? Yeah, you don't. So what we use this for is strictly between 2 atoms. So in the case of water, what you would do is you would do it for the oxygen, the hydrogen. It happens to be obviously the same value here. So you would do it for each set of 2 by itself. So we use the difference in electronegativity simply between the 2 elements. And it will tell you, in a compound, not just necessarily like water, but in other compounds, you may have a bond that is polar. You may have another bond that's non-polar. So it's just between the 2 atoms. Yeah. Other questions? So why don't you try some here? Why don't we do, I'll put them here. Based on the electronegativity value that's here, which obviously would be provided for you. You do not need to memorize this. Yeah. Are these going to be polar, non-polar, ionic? Let's do potassium and chlorine. Let's do carbon and oxygen. Let's do sulfur and oxygen. Let's do carbon and hydrogen. And let us do carbon and sulfur. All right, so use the electronegativity values here to determine, is it polar, non-polar, or ionic here? Let's take a look, see. So we'll start here with our KCl. Really don't need the numbers. This should be what? This should be ionic, right? It's a metal and a non-metal, but just to play along here, we'll go with 0.9, I think, for the potassium, and our chlorine is 3. So the difference in electronegativity going to be 3 minus 0.9 at 2.1, which obviously, again, is above 2, so it's ionic. Takes care of that one, I think. Let's do carbon and oxygen here. So carbon is 2.5, looks like. And oxygen here is 3.5. So our difference here in electronegativity going to be 3.5. Above 0.4, but less than 2. So this should be polar. The arrow should point towards which element? Should point towards the oxygen as it is more electronegative. Yes, that way. Take care of that one. Let's do our sulfur and oxygen. So sulfur there is 2.5 as well, looks like, and 3.5. So again, our difference in electronegativity here going to be 3.5 minus 2.5, which gives us 1. Once again, that would then make this a polar bond. with the arrow pointing towards the oxygen side that's more electronegative. Obviously meaning that they are sharing the electrons unequally here, right? In this case. Our carbon hydrogen there, carbon is 2.5. I think hydrogen is 2.1. Difference in electronegativity going to give us a 0.4. That means carbon hydrogen is nonpolar. That is the cutoff for nonpolar. And it's cut off because of that bond. That's pretty much the bond you find in organic chemistry and organic molecules like heptane you used the other day. Yes, the smelly stuff is organic, it's nonpolar, and that's if not, there would be no organic chemistry. So nonpolar here, equal sharing of electrons in this case, basically no arrows would be drawn. Then we got our carbon and sulfur. We'll go down here to do it. Carbon is 2.5. Sulfur here is 2.5. So when I subtract that, I get a 0 happening. Means it is what type of bond? It is nonpolar as well. So this is a very good example that you can have two different elements that actually are nonpolar. They will share their electrons equally. If you have two of the same elements, they definitely will share them equally, but you can have it that they will share it unequally. The reason for that is actually what is sometimes referred to as the diagonal rule. Carbon is further up, but sulfur is further to the right, so they cancel out their differences in terms of electronegativity. Same thing over here with nitrogen and chlorine. There's a couple of places there where not right below, but kind of down and to the right, they sort of cancel out their differences, and they actually could end up with the same electronegativity value and give you something that's 0. So if you find two elements that are diagonal each other on the periodic table and you don't have the table available to you, you know, if they're down and to the right of each other, they might be the same. So you want to keep that into consideration. People always say sometimes like, hey, I can't do this. I don't have the numbers. You don't always need the numbers to do this or make an educated guess. You can use the general trend in electronegativity to make a fairly educated guess as to whether or not something is going to be polar or nonpolar. For example, if we look at this one here, that's carbon and oxygen. Carbon is right here. Oxygen is right here. They are in the same period of the periodic table, which means further to the right is more electronegative, which means because they're in the same row, it's a safe bet that's going to be polar. Yeah. We could also look at our sulfur and oxygen. Sulfur is here. Once again, oxygen is right there. They are in the same group on the periodic table. And as you go up a group, the electronegativity increases. So once again, you can make a pretty safe estimate that that should be a polar bond. So you don't always need the numbers. You can use the general trend a lot of times to make a pretty safe guess. If you are comparing two elements that are in the same row, and they're basically are not in the same spot, which they would not be, that's probably going to be polar. And if they're in the same group, is going to be a polar bond. And that's a good way to just use the general trend. Any questions on how to use this here? This is what is sometimes referred to as bond polarity, where you're just simply going between this atom and this atom. Are they going to share those electrons equally or unequally? And that is sometimes what is referred to as bond polarity. Molecular polarity, we'll talk about later, where you take basically everything into account in the entire molecule. So as we saw here, atoms with really big difference in electronegativity tend to lead to ionic compounds, electrons being transferred. While when we get basically guys in a similar location on the periodic table, like what we have with covalent bonding, that they're all sitting right there in the non-metal region, they all have very similar sort of properties about, I want to hang on to my electrons and I would like your electrons. So as I mentioned earlier, the best that we kind of can do is they decide to share rather than transfer electrons in that particular case. And obviously, that's what we talked about so far: ionic bond, metal, non-metal, transfer of electrons, and our sharing of electrons there in our sort of covalent bond. The top rule is what we were talking about, the cutoff for 2 and the 0 to 0.4. occasionally, sometimes people talk about bonding in terms of percent ionic character, and something with 100% ionic character is pretty much an ionic bond. Something with 0% ionic character is actually a pure covalent bond, a nonpolar bond, equal sharing of electrons. So occasionally that does pop up, as you can see here. Purely covalent, purely ionic bond here would be 100% ionic character. This would be like 0% ionic character. And obviously our kind of unequal sharing of electrons would be somewhere percentage-wise in between 0 and 100. Would give you some type of a little bit of characteristics of both, basically. So let us then talk about really an important thing here, which is how you go about drawing Lewis structures for covalent bonding. So we did it for ionic bonding earlier. This is how we're going to draw it for things that share electrons. It's a little bit different than what we do with covalent ionic bonding. The first really important thing is you want to think about logically how the molecules sort of put together. And to help you decide that, usually the center atom is the least electronegative atom. So the least electronegative atom is usually in the center. That means that we never find fluorine in the center because it is the most electronegative. And as our conversation earlier, we'll never put hydrogen in the center because it will have multiple bonds, right? And more than 2 electrons. So those guys will never find themselves in the center. I would say most things that you draw in here, not all things, but most things will have one guy in the center, everybody else attached to it. Now you can't have multiple center atoms and things attached, but probably in here, most of the time, one thing in the middle, everybody else sort of attached directly to it. Number 2 is probably the most important thing, which is you need to count up the total number of valence electrons in the entire molecule or ion, if you're doing like a polyatomic ion. That comes from the periodic table. The number of valence electrons equals the group number. This number is really important because when you get this number, you got to have exactly that number on your picture, no more, no less. And if it does have a charge, you need to adjust your count of electrons. So if something has a positive charge, it means it has lost electrons. So you need to subtract that from your total. If something has a negative charge, it means it gained electrons. So you need to add that to your total. Once you got sort of the logical arrangement going on and how many electrons, you're basically going to make one single bond from the center atom to each of the outside atoms. Use lines, but if you want to use dots, you can, but I would use lines. Once you do that, each line represents 2 electrons. So you used up a number of electrons in doing so. You will still have electrons left over at this point. The leftover electrons always go to the outside atoms in pairs of electrons, so pairs of dots. And to each of the outside atoms has 8 electrons, unless it's hydrogen, then it should be done. And then you should fill up all the outside atoms with dots. If you still have electrons left over at that point, you go to the center atom and you put dots on the center atom. At that point, you should be out of electrons. If you still have electrons at that point, you did something wrong. So you should be out of electrons at that point. The last thing you want to do is make sure everybody has met the octet rule, except for hydrogen. And it's really at that point, if somebody does not meet the octet rule, that is when you want to try to fix it by making a double bond to fix it. And you want to sort of exhaust all your double bond options. And then if by some chance the double bond, then you roll to a triple bond and try to fix it that way. So again, you don't want a double bond or triple bond out of the box. Save it. So a lot of rules. Let's go through this one together here and show you how we go about it. We're going to do NF3. So the first thing we're going to do is calculate the total number of valence electrons. So nitrogen is group 5, which means it has 5 valence electrons. There are 3 fluorines. Each fluorine is group 7, which has 7 valence electrons. That is 21, and 5 is 26 valence electrons. So that number is important because my picture needs to have 26 exactly. Nitrogen and fluorine are in the same period. Nitrogen is further to the left, which means it's least electronegative. So it's going to go in the center. I'm going to put a fluorine on each side, and I'm going to go one below. Could you put the third fluorine on top? The answer, yeah, it don't matter. You could put it on top, you could put it on the bottom. It really doesn't matter. Once I have my logical arrangement, I'm going to do from the center atom to each of the outside atoms. Each line represents 2 electrons. How many total electrons have I used so far? 6. I can subtract it off my total. That means I got 20 electrons still to go. Electrons are going to go on the outside atoms in pairs. So 2, 4, 6. That is now filled because it has 8 around it. 8, 10, 12. That is now filled because it has 8 around it. 14, 16, 18. That is now filled because it has 8 around it. At this point, I have now placed 24 electrons, right, on my picture. That means, technically speaking, I still got 2 more to go. Those 2 now go to the center atom, and we lay it up there as dots as well. At this point, we now have 26 electrons on our picture. The last thing we want to do is make sure that everybody has met the octet rule. This fluorine has 2, 4, 6, 8. Each of the fluorines are identical. They all have 2, 4, 6, 8. 2, 4, 6, 8. Nitrogen has 2, 4, 6, and 8. Everybody has 8 valence electrons around it. That would be the correct picture without the highlighting, I imagine, but that would be the correct picture there for NF3. Any question on those steps? If you follow those steps, you will probably get the right picture. If you do it by piecework, where people like draw nitrogen with 5 dots and oxygen with 6 dots and try to figure out how they come together with covalent bonding, what usually happens is you'll end up with the wrong number of electrons, wrong bonds, and stuff like that. If you follow this, this should lead you to a pretty good picture. To gain an electron, so that's an 18, 19, 24 valence electrons here. Logical arrangement here, nitrogen is least electronegative, and there's only one of them, so we'll put it basically in the center. We're going to do our single bond from the center atom to each of the outside atoms, and again here we use 6. There's a lot of math there. I'm going to go with 18. We got 18 electrons still to go, so we're going to go with 2, 4, 6, 8, 10, 12, 14, 16, 18 at that point. At this point, we have now put up 24 electrons. Is everybody good in this situation? No, it is the nitrogen that's a little short here. Nitrogen has only 2, 4, and 6 electrons, right? Everybody else has 8. So this is a case where we want to fix it. Can I fix it by just doing that? I cannot, although it does fix the problem with nitrogen. Now, how many total electrons do I have? 26, which is no good. So I do want to fix it by making a double bond. And in this particular case, all the oxygens are identical to each other. So you can really make the double bond in any oxygen you like. Can I just draw another line in there? I cannot, for the same reason. I now have 26, and that poor oxygen up on top's got 2, 4, 6, 8, 10 electrons. That's a lot. Too many for the oxygen. So when we make a double bond, what we're actually going to be doing is, put this back. We're going to take a pair of electrons, in this case from any of the oxygens, and we're actually going to bring those electrons in to make the double bond. So I'm just going to take it from the top there. When I do it from the top, I will end up with a double bond that forms up on top. The single bond will remain there on the left and right-hand side. And I'll put a little bracket around it because it does have a charge, is typically what we do. And we put the little negative on the outside. Now at this point, by making that double bond, I still have only 24 electrons. My oxygen here is 2, 4, 6, 8 is good. This one is 2, 4, 6, 8 is good. Double bonded oxygen 2, 4, 6, 8 is good. And now our nitrogen 2, 4, 6, 8, it is good as well. So we're able to maintain the right number of electrons and also have the right number of bonds to do that. Now you could have, as I mentioned, double bonded at either one. So you could have left it like we did here. You could have double bonded it to the right, which would have gave you something that looks like this. Or you could have double bonded it there to the left, which would look something like this. Not like that. I mean, it would have looked something something like this to the left. All these structures are actually related to each other. They're all what are known as resonance structures. And resonance structures basically occur like we see here in a situation where there's more than one place where you could do the double bond. And that is because these double bond electrons that we kind of moved in, they're what are referred to as being delocalized, which means at any given time, they could be over here by this guy on the left, could be on the guy at the top, could be on the guy to the right. So the real structure is somewhere between probably all three of those. And you could draw an equivalent resonance structure for any of them as well. Now, if you're asked just to draw the Lewis structure, you could lay up any one of the three drawings, just be perfectly fine. Either one of the three is fine. If you're asked to draw resonance structures, you should all three of them. And resonance structures are usually indicated one from each other by these arrows that kind of head in both directions. But again, if you're just asked to draw a Lewis structure, any of the three would have been sufficient in this case. Yeah. Any questions on any of that? Okay, yeah. Where did I get the? That's the number of valence electrons that equals the group number. So nitrogen is group 5. And oxygen is group 6. So the number of valence electrons equals the group number. Yep.